When we design things, we are almost always thinking about at what point will they fail? Because once we know the failure point, then we can figure out how can we stay back away from that failure point. So we might be thinking about how much load, and thus how much stress, can something carry before it yields or breaks or buckles or deflects too much. And we'll look at each of these are the failure modes. We'll look at each of these failure modes one by one. Here are some lab samples that display those various modes. And here on slide 3 is a summary of what each of these failures means. First of all, let's think about why do parts fail? What is going on? When we're thinking about why does a part fail, we'll think about these basic ideas. What type of stress is it? What type of material is it? What type of load did it experience? And are there any cracks in the material? What type of stress did it receive? Well, you might recall that there are 4 kinds of stress. Tension, where it pulls, compression, where it squeezes, shear, like scissors, and torsion, which is twisting. Here's an example of an axle that failed in torsion. Remember what you know about ductile materials versus brittle materials. So this is an idea that relates to failure modes. And ductile materials are ones that give warning of impending failure. And what does that mean for us with our stress-strain diagram? It means that when we reach the yield point, let's say in mild steel, we reach the yield point and suddenly there's a plastic range, isn't there? The steel suddenly begins to stretch and get longer and longer without any increase in load or stress. It's like silly putty, and it is stretching out. It has yielded. It's beyond the elastic limit, so it's not coming back, and that gives us a chance to get out of there before it finally breaks. A brittle material, such as concrete or cast iron or dry spaghetti, gives no warning of impending failure. Things look fine until all of a sudden it just fractures. You don't see any plastic deformation happening first. So let's think about failure criteria. And by the way, just a note about this word. Criterion is singular, so we have one failure criterion. Criteria is plural, so we have one criterion for criteria. That's why there are 2 different forms of that word. And you will sound like a college-educated person if you use criterion for single things and criteria for plural things. So the criteria for these kinds of materials, for a ductile material such as mild steel, we consider the yield point to be the failure point, don't we? So once it is yielded, it is no longer functioning as intended. It has failed, even though it hasn't broken yet. For concrete, we think about the compressive strength, and you might remember we've looked at test cylinders for concrete samples and how we send them to the lab and compress them in a press and see how much load it takes for them to explode. Then here are a couple of others. Elastomers means rubbery things, and composites, we think about tension. So ductile materials, such as good old mild steel. As you might recall, ductile materials tend to fail in shear. And what happens? First, you get some plastic deformation. First, you get the thing going past the yield point. These molecules slide past each other at 45-degree angles. The thing starts to turn into silly putty. It starts to stretch. It has yielded, and then eventually it will fracture. And recall that when a ductile material fails in shear, the shear plane, the fracture plane, is at a 45-degree angle. And this picture on the left is a perfect example of that. Here is some steel rebar, and you can see that is a great big piece of rebar. This was out of a freeway bridge down in the Bay Area when that 1989 earthquake struck. And this big piece of rebar failed in shear, and there is that perfect 45-degree fracture face there. And then here are some supporting columns. You can kind of see 45-degree faces in some of them. Brittle materials like concrete, we often test in compression, and we give the concrete strength in compression. Here is a photograph of a concrete test cylinder in a hydraulic press at the moment that it fails. So here are some test samples of failures. Here is some ductile steel that failed. See that 45-degree angle on the cup and cone when it was pulled and it pulled apart, as opposed to cast iron, which is brittle. When it was pulled and pulled apart, it's got a vertical fracture face. Then this bending test is kind of interesting. Here is an illustration of the difference between ductile and brittle. If you bend a piece of steel until it fails, what happens? It yields. Looky there. It has yielded. It is not coming back. It has gone past the elastic limit. You will never be able to straighten that thing again. It's not possible. It has failed. Whereas a piece of cast iron, which is brittle, when it fails, it stays straight, everything looks fine until all of a sudden, boom, cracked, came apart. Another thing we want to ask is what kind of load was there? Was there a static load, a load that didn't move and it just stayed the same? This will be especially relevant when we look at creep failure. Was it a dynamic load? Maybe it was just one sudden load that hit with an impact. Maybe it was a dynamic load, a load that moved over and over again. It repeated. And that will be especially relevant when we look at fatigue. Now let's look at the various failure modes. And I think we'll just look at a couple of failure modes. Elastic and the other one, and then we'll stop this video and we'll come back and start fresh with a new video. So elastic failure, this one, okay, it's a failure because the object is not functioning as intended, but it's not disastrous. This is the kind of failure you find if you're walking on the second floor of a building and they have used joists that were not stiff enough. They were strong enough so they're not going to yield and they're not going to break, but doggone it, they're awfully springy. It's like walking on a trampoline. That is a kind of failure because nobody likes that. It makes you feel creepy, like, something might happen here. But it has not passed the elastic limit yet. One bad thing that can happen is plaster in the ceiling underneath could crack and fall down, and that could cause damage or injury. So how do we prevent elastic failure? We are looking for stiffness. And as you recall, there are two properties that control stiffness. One of them you already know about, the stiffness of the material. How floppy is this material? What is its modulus of elasticity? Rubber is more floppy than steel, which is more stiff. In 2 or 3 weeks, we'll look at the stiffness of the shape, the moment of inertia. So we're looking at stiffness in order to prevent this elastic failure. Yield failure is what happens when you reach the yield point on your stress-strain diagram. I should have put a diagram here. Remember that point on your diagram when you've reached the end of the sloping straight line and now the graph suddenly turns horizontal and starts going into plastic failure? That's the yield point. That's the point where we have gone past the elastic limit and we are not coming back. And you may be familiar with this if you've ever pounded a nail and had it bend like that. That is yield failure. I don't know if you've ever worked for an employer who said, well, we want to save money. I want you to take these bent nails and pound them out straight again and we'll use them again. I've known of a couple of organizations in town who did that. What's wrong with that? Well, that nail has already yielded. So you can hammer it out kind of straight, but you will never get it straight, and you will always have that yield failure where it bent, so it will never ever be a good nail. But we can also use yield failure intentionally when we're forming sheet metal and plate or making car parts. Oh, I wanted to point out another example of yield failure happens if you over tighten a nut. So in some situations, particularly structural steel, there are torque values, and you're supposed to torque the nut to this number of foot-pounds or inch-pounds and stop. What happens if you over-torque that nut? What happens is, look at this necking down picture at the bottom, you stretch the threads, you stretch that bolt, you cause that bolt to yield. It goes past its elastic limit and goes into plastic mode, and now that bolt has stretched out and the nuts actually get looser because you over-torqued. It's kind of interesting. And yield is caused by dislocations, these molecules slipping past each other. Finally, the ultimate kind of failure is it broke. It broke in pieces. That's called fracture, and when we look at our stress-strain diagram, that's the ultimate stress at the peak of our stress-strain diagram. This is what happens with brittle materials like cast iron and concrete. All right, let's stop here and we will come back next time and talk about creep.